Hello! How are you doing? Ready for one more day? Let's learn about the multiplication principle. Can you multiply? Hope so. So our multiplication principle in combinatorics is the following idea. Suppose you have to complete task A, and there are NA different ways of doing this first task A. Okay? Whatever is the task, this is a positive integer number, n, 1, 2, 3, 4, okay? So then you have to also do a task B. For task B, you have n index B different ways of doing task B. Then so on and so forth until you make a final task, task C, where you have NC different ways of completing the task C. And the problem asks how many ways can you do everything? Task A, task B, etc. up to task C. Okay? And the answer is you guess it. You multiply. Multiply NA times NB times etc. times NC. Okay? So you can do all tasks in A times NB times etc. up to NC. Okay? You have this many ways of doing all the tasks. Let's see an example. Things are much easier when we see an example. So suppose you are here in city A, location A, and you have two different roads from going to city A to city B. And from B to C you have three different roads. Okay? So how many ways can you go from A to C without returning? You always have to move east. That's a condition on the problem. Okay? So to do the first task, you have to go from A to B because there's no direct road from A to C. So you gotta stop at B, pass at B in the middle of your journey. Okay? So you have two different ways. You can go use this road or you can use this road. So you have two different ways of doing the first task. The first task is going from A to B. And then from B to C is the second task. How many ways can you do the second task? Well, you have three different roads from going from B to C. So you can do this task in three different ways. You can use this road, you can use the middle road, or you can use this south road here. Okay? Overall, how many ways can you go from A to C? You multiply 2 times 3. There are 6 ways. That's the answer to the problem. Okay? You use the multiplication principle, multiply 2 times 3 and find 6. Okay? Another very interesting problem, this tea room problem. Do you know the tea room problem? Very famous problem. So this is the tea room, the plan of the tea room. And let's look at the doors. There's 1, 2, 3, 4, 5 doors. Okay? So the tea room has 5 doors. The problem asks in how many ways can a person enter the tea room by a door and leave by another door, by a different door. You cannot use the same door that you enter to exit. You have to exit by a different door. So, in how many ways can you do it? Let's solve the problem using the multiplication principle. You have to do 2 tasks here. You have to enter and you have to exit the room. How many ways can you enter the room? Well, 1, 2, 3, 4, 5 doors. There's 5 ways to enter the room. And in how many ways can you leave? Can you exit the room? You cannot use the same door that you use to enter to exit. To exit, you can only use the 4 other doors. So you have 4 possibilities, 4 choices, 4 different ways to exit the room. Doesn't matter the door you use to enter, you cannot use the same door to leave it. So you have only 4 options. All in all, you use the multiplication principle to do both tasks, to enter by a door and exit by a different door. You have 20 different ways of doing that. That's the solution, 20 ways of completing this tea room challenge, if you like. Okay? Now that you are happy about that, let's talk about my good old friend Joe. This guy is fantastic, Joe. So look at Joe. He's naked here. I blushed. So Joe needs to dress up. He needs a hat. He has 3 choices of hats to use to cover his head. He needs a t-shirt. He has 5 choices. He needs a pair of pants. He has 4 choices. And he needs a pair of shoes. 2 choices. He doesn't use socks or underwear. Okay, so in how many ways can Joe dress? To do the first task is to choose the hat. He has 3 options. The second task is to choose the t-shirt. He has 5 options. Then he needs to choose the pants, the pair of pants. 4 options, 4 different ways of doing this task. And to choose the pair of shoes, he has 2 possible choices. Overall, the solution is 3 times 5 times 4 times 2. 5 times 2, 10. 3 times 4, 12. Joe has 120 combinations. 120 different ways to dress up. Okay? So 4 tasks, and you multiply the number of ways to find your solution here. Okay? And now let's try another fantastic problem. It's a competition, the Olympic Games, the competition. Look at that. We have 3 medals. The gold medal, everybody wants the gold medal. The silver, and the bronze medal. Okay? So you have 3 medals and you have 8 competitors in the final. In how many different ways can we give these 3 medals to the 8 competitors? Okay? Well, we have what? We have 3 tasks. We have task 1, we're going to give the gold medal to. The second task is the silver medal, who we are going to win the silver medal. And the third task, we have to give the bronze medal to someone. But the same athlete, of course, cannot win more than 1 medal. And since we have only 3 medals for 8 athletes, 5 athletes will end up with no medal. Okay? Let's think about that. Here in the blue, it's the gold. I write the name of the person who wins the gold. In how many? Here in red, the silver medal. And in green, we have the bronze medal. Okay? So in how many ways can we do the first task? The first task is to write the name of one of these athletes to win the gold medal. How many options I have? 8, right? I can do this first task in 8 different ways. Now, once I write the name here for the athlete that wins the gold medal, this athlete can no longer win another medal, a different medal. So how many ways can I choose the name of athlete to win the silver medal here? Well, the 7 remaining athletes are still competing, so I have 7 different ways of choosing an athlete besides the one who won to get the gold medal. Okay? And since 2 athletes already have medals, how many options I have for the bronze medal? I have 6. Okay? So all in all, I will have 8 times 7 times 6 ways of giving the medals to gold, silver, and bronze. Now, by the multiplication principle, okay? Notice that this problem is going to be different than the problem below. The next problem asks you to choose a committee of 3 students, exactly 3 students, in a classroom of 8 students. So the classroom has 8 students and I have to choose 3 students. Now the problem is different because for a committee it doesn't matter who is first, who is second, and who is third. The order of the chosen students make no difference for the students. They are equally important inside of the committee. Okay? Things would be different if I were to say, oh, I have a president for the committee, but I won't. Forget about that. The three members are equally important inside of the committee. Okay? So I can do that in how many ways? Well, I could start by imitating this problem, but then I have an issue in which if I say I choose student A first, then B, then C, or I choose A first, then student C, then student B, or student B first, then A, then C, or if I choose B first, C second, and A third, the 6 possibilities, right? The 6 permutations of the tree. Here, in this initial problem, I'm counting these 6 possibilities as truly different possibilities, right? Because it's different if you get the gold medal or the silver medal or the bronze medal. If Johnny gets the gold medal, Johnny is super happy. If Johnny gets the bronze medal, he's not that happy anymore. Okay? So the order matters, but here the order does not matter. Okay? So the solution for this problem here would be 8 times 7 times 6, but I have to make a correction because of the order thing. Here I illustrated the fact that every 6 different choices that I have, they actually represent the same choice. Students A, B, and C were chosen in all these 6 possibilities. Therefore, I have to divide by 6. But this 6 here, I'm going to write this 6 as 3 times 2 times 1. Why? Because I want to write this as 8 factorial over 5 factorial, 3 factorial. Okay? And this is exactly what we call the binomial symbol 8 choose 3. Okay? So how many committees of 3 students can we get when we have 8 students? Well, it's 8 choose 3. In general, n choose k is going to be n factorial over k factorial n minus k factorial. This is always going to be an integer number, by the way. You can prove that. But this means you have a group of n students and you have to choose a committee of k students. And the order here of the students does not matter. So I should say order does not matter. And once I choose one student, I cannot choose the student again. So this is no replacement. There is no replacement. Okay? And this is what we call n choose k. Or more formally, this is the binomial coefficient. Okay? The binomial coefficient, n is a non-negative integer, k is a non-negative integer, smaller or equal to n in principle. Okay? And we define the binomial coefficient this way. Right? So that's here in this first problem of the medals, this solution here is not the binomial coefficient. This is going to be 8 choose 3 times 3 factorial. Okay? So I can write this as 8 factorial over 3 factorial, 5 factorial times 3 factorial. And then I cancel this 3 factorial, so I end up with 8 factorial over 5 factorial. which is exactly this. It's 8 times 7 times 6. I cancel the 5 factorial on top and bottom. Okay? So in this case here, I still have no replacement. Once you give a medal to an athlete, you cannot give a different medal to the same person. The maximum an athlete can win is 1 medal. Okay? But here, the order matters. The order is important. Okay? You want to be gold. If not, you want to go be silver. If you change the order, like in this, you change the result of this problem here. Okay, but not here. Here the order does not matter, and you can only apply the binomial coefficient directly to this kind of problem. But for this kind of problem where the order matters, you have to make an adjustment to your problem. Okay? And now let's see how a mouse can get to the cheese. That's a very philosophical question. In life, we are all like little mouses and we are all chasing our favorite cheeses out there. So let's see how it goes. Here's the mouse. Doesn't look like, but believe me, it's a mouse. And the mouse has to walk a path here. This red one is just an example, could be a different one, to get to the cheese here in the top right corner. Okay? So the mouse can only walk along the blue lines. And the mouse can only move to the right or up, which I'm going to call right east and up north. Okay? So that's the only way, because you can think the mouse is smelling the cheese, so it's never going to go back or down. Okay? Never going to go to the west or to the south. The mouse always goes to the right or up, east or north. How many paths can you find? So this in red is an example of a path, but of course there are lots of other paths. The mouse could do this, it's another path. The mouse could do this, it's another path. There's lots of possibilities. How many possibilities? That's the problem. Okay? Can you do it? I'll give you a solution in 3, 2, 1, now. The solution is, for each of these paths, let's give the instructions, let's write down how the path is going. For instance, each path I have to move to the right, to the east 7 times, and to the north 5 times. 1, 2, 3, 4, 5 times. Okay? So to the east I have to move 7 times, and to the north I have to move 5 times. Okay? So overall, each path, I have to do 12 moves, okay? 7 moves to the east and 5 moves to the north. So I'm gonna write down here, in these 12 boxes, I'm gonna write one of the possible paths, just to illustrate, okay? So let's do this one here, in the middle. So here, first I go north. Okay, so first I go north in the first step. Then I go twice east. So the second step is east and the third step is east. Okay, then I go north twice. North and north. Then I go east 1, 2, 3, 4 times east. 1, 2, 3, 4 times east. Then I go north twice. And then finally I go east once. Okay? So each path corresponds to a word having exactly 12 letters, and out of which 7 of these 12 letters are going to be E, and 5 of these letters will be N for north. Okay? So now I just have to count how many of these words I have. the set of words that I can write like this is equal to has the same number of elements as the number of paths. Okay? It's a bijection, it's a one-to-one correspondence. Okay? So, how many words? So that's anagrams with repetition. Watch my video with anagrams with repetition. There's a bunch of exercises in the theory I explained there. But here I'm going to explain in a different way. So I have 12 places where I have to choose the 7 positions that are going to be east. Okay? The 7 positions. In how many ways can I do that? Well, 12, choose 7. After I complete this task, after I chose the 7 positions where I write the E, I'm essentially done. All the places left I have to put an N, but then I have no 2 different ways of doing that. I just complete with the N's in the 5 positions that are left. Okay? And how much is this? Well, this is 12 factorial over 7 factorial, 5 factorial. Okay? Is the number of anagrams of this word here. A word with 12 letters, 7 letters E, and 5 letters M. Okay? That's how we do it. So that's this beautiful trick of transforming this problem about mouses and paths into a problem with anagrams and using our binomial symbol to solve the problem. Okay? Very sophisticated technique. Hope you enjoyed the video today. See you next time. Bye bye.